Nice. So homework 5 here is posted, and I want that on Tuesday. It's 8 problems, but some of the problems will take more than 1 page. So you want to finish it on the back, right? And so you might have to rewrite it. It might take you 3 pages to do the problem and then rewrite it so you fit it on 1 page, front and back, okay? So still 8 pieces of paper handing in. Our schedule for starting today, week 10, right? We're going to have a quiz on Thursday on 6.2, only on 6.2, right? I'll ask you to find me an absolute min or max of a function, and I'll ask you to find me critical values.
You mean 4.2?
Yes, 4.2. I keep doing that. So dumb. Week 11, next week, you're going to hand in homework 5, right? And the other thing that's really important is that our week 16, Tuesday, Thursday, that is May 9th and May 11th. May 9th, there's no class. And that's true for all of your classes. The day you have your exam is the only day you go to your class on that last week, okay? And so our exam is on that Thursday from 8 a.m. to 10 a.m. A little bit strange, right? Because we're used to starting at 9. On that one day, we start at 8, okay? And I'll be here an hour early to open the door, and I'll be here 15 minutes early, right? To get everything passed out to you so that you can take the exam right at 8.
8 a.m.?
8 a.m. And I'll try and remind you for the next 5 weeks that it's at 8 a.m., right? Good. Questions for me on anything here? Any questions for me that you've been practicing in the book and you need help with? You need to be practicing, okay? You really have to practice this stuff. It's not that it's difficult. It's not difficult. Every step is easy, but it's long. The process is long, right? So you have to have the process down. You have to practice. You can't just watch me do problems. You can't watch me parallel park and then parallel park. You can't watch me play guitar and then play guitar. You have to sit there and work on it on your own. I think I still know how to play guitar anyway. So no questions for me to do from anything from 4.2, 4.3. Also, what should you be doing? All of my chapter 4 exams, right? Start working on them. After this week, we'll be done with chapter 4. And all of my final exams that include the chapter 4 material, right? Good. Let's do a first derivative test. Yes? Ready? So I want to use an f prime test on f of x is equal to the arctan of x squared. So we want to find everything we can about this. We want to find the intervals where it's increasing, the intervals where the function is decreasing, if there are any mins or maxes, right? Local mins or maxes, yes? So first thing we said we always do is graph this, right? If I go back to pre-cal for a second and graph just the plain old arctan graph, here it is, pretty easy. And kind of a boring function to do a first derivative test on because what are you seeing from the graph? Say it again.
1 min and 1 max.
Okay, so this if you remember from arctan, right? It never ends, right? So it goes so the actual min and max are happening at infinity, so we don't bother with it, right? And we know the range is from minus pi over 2 to pi over 2 exclusive. Yes? Just lie to me and say yes. Well, so I mean, we're related this to tangent, right? Here's our tangent function, and that's from minus pi over 2 to pi over 2 in domain. So the inverse function is from minus pi over 2 to pi over 2 in range, right? Inverse functions trade inputs and outputs, right? So kind of boring for the first derivative test because it's always increasing. Do you see that? Do you see this arctan function is always increasing, right? And so there's no min or max there, right? There's no local min or local max. But if I change it to the arctan of x squared, I get this function. And so different, right? Definitely it's decreasing at first, right? Then increasing, and there's a local min, right? Do you see that? Bottom of a valley. Yes?
Wait, what is the purple one?
The purple one is just arctan. Right? And the green one is tangent. So we're dealing with this red curve, right? For first derivative test. I already know all the calculus. I know the first derivative is negative on the interval from minus infinity to 0. And that means the original function is decreasing on that same interval, right? I know this first derivative is positive on 0 to infinity, right? Because I see that the function is increasing on that interval. And I know there's a local min at 0, 0, right? So, but now we'll do the calculus. Yes? So first step is to draw the graph, find the derivative. Yes? So if you remember, if y equals arctan of u, y prime is u prime over 1 plus u squared. So I need to find u, I need to find u prime, I need to find u squared, and plug and chug, right? So what's u for me? X squared. What's u prime? 2x. And what's u squared? X to the fourth, right? Good. And my derivative is, so y prime is 2x over 1 plus x to the fourth. So there's my derivative. Easy, yes? Say again? I don't need it in this particular case. And so remember, if you start working on this, you'll see none of these first derivative tests need the triangle on anything. But you know, if you got somewhere and you needed a triangle, you certainly could create it, right? On the inverse trig problems I was having you do, I said get the triangle right away. You might not need it, right? So here I'm saying you don't need it. But I need to find my critical values, right? Yes? So critical values are when y prime equals 0, which means 2x equals 0, right? Which means x is 0. Yes? Y prime does not exist means 1 plus x to the fourth equals 0, but that can't happen, right? Right? So no other criticals. How are we doing here? We're okay? Good. Now I'm going to do my number line, right, with my domain and my critical value of 0. I need to test left of and right of and in between all my criticals. So it looks like a -1 should work for me, right, and a +1. And so, of course, I'm testing f prime at both of those. I don't even need to bother doing it, but you should see if I plug in the negative down, positive or negative downstairs, it's always positive. So it's just the numerator is the only thing affecting the sign, the SIGN, right? So negative and positive, right? So I'm actually plugging in the -1 into the numerator and I get -2, right? So that's where my derivative is negative. I don't need to do that. I can just look at the function, right? I can just look at that red curve and say, oh, look at it, it's decreasing. That means the derivative must be negative, right? Good, it looks like I'm ready for my conclusion. I do need a little bit of work. I'll do a little side work and in that finding that f of 0 is arctan of 0 squared, which is 0, right? So I know that point exists, yes? and I'm ready for my conclusion. F prime is negative on minus infinity to 0, so F is decreasing on the same interval. F prime is positive. Yes, we're okay here? Yeah? On 0 to infinity, so F is increasing on the same interval. F prime changes signs at x equals 0, right? F prime changes signs from negative to positive. Oops. To positive, right? At x equals 0 and 0 comma f of 0, which is 0 comma 0, is real, right? It's a point, yes? R squared is xy plane, right? So I need the derivative to change signs, and I need the point on the original function to be there, right? So 0 comma 0 is a local min. Done.
I have a question.
Yes, I have an answer.
So like for a number line, and like when we are writing the conclusion, like for negative
Yep, negative infinity to 0.
so like do we need another like
But you got to let things happen. You don't. Let's not make things up. Let things happen. There's only one interval where it's decreasing, right? Look at the curve. Look at the red curve. There's only one place where it's decreasing.
yeah.
So let this test tell you what the interval is.
I mean like
I know what you mean. I don't want to go there. I don't want you to go there. I'm going to do a second derivative test. We'll have more than one interval. That's what you.
you know what I can go to that?
Yes.
Like
I know what you want. I'm not. Let me do.
no.
Because I have magic powers. So let me do the second derivative test, and you'll see it'll happen. What you want to happen will happen in my next problem. Okay? Thank you. Everyone okay? Yes. Just the conclusion, right? Yes. And the conclusion is of course the worst part of this, right? Because we don't want to write. We're a little lazy, aren't we? I am anyway. R squared. So I need the point to exist. So I'm saying it happens on the xy plane, right? Yeah. Yeah, you could do R cross R, right? You could say x. No, so you'll see when I do conclusions, I'm trying to do them a different way every time, so you see your options. Yeah. So you could just say, and the point exists, right? That's enough, right? Good. Ready for a second derivative test? Yes? Min, almost? Yes, question? The third point?
Right after the end, you could just say it exists.
Yes, the point exists. Yep. And so like second derivative test, I'm going to be finding inflection points. So I get my critical values from the second derivative, but I make sure again I am finding the point in the original function, right? So, and the name of the test gives you the hint, F prime test. You're testing with, yes. There's plenty of times when my derivative will change signs, or my second derivative will change signs, but there's no point there. And I did an example like that in the last video. Yes.
So why is there is that a real number, right?
Yes, or it's a point. Yeah, the point exists.
So why do you need a square?
R squared is x-axis by y-axis. So it's real numbers crossed with real numbers. So we say all the real numbers squared. It's just me being nerdy. Don't worry about it. Just say the point exists, okay? Good, let's do a second derivative test. So f double prime test, meaning I have to test values in my second derivative. But I find points in my original function. So I use my favorite function. This is on every single chapter 4 test I've ever given, e to the minus x squared over 2. So we've seen something like this before in this class. And that's what you have to also realize what's happening. We're learning new stuff, but all of these old functions are coming back again, right? So they're never, in fact, they're never going away. They're going to go all the way through differential equations for my engineers, right? For the rest of us, Calc 2. Computer scientists, we'll see some of them in linear. Biologists done after Calc 2, right?
So we need a second derivative for the
No, I asked for a first derivative test.
Oh.
But if you're smart, you'll do the second derivative test with that same function. In fact, you'll see it on one of my old exams, right? Okay, so here we go. First thing, graph the function. We know what this thing looks like. It's a bell curve, right? If you drive on that road for me real quick, do you see that you change your steering wheel twice? Can you drive on that road left or right for me? Yes, drive on the road, turn the wheel. Yes, so 2 inflection points, right? You with me there? What's the concavity start? Say it again. So it's how many times your steering changes. So if I'm driving on this road, remember it's not a hill, it's a curve, right? So I'm starting by steering to the left, and then I come back and turn to the right. That's a 1 change. And then I come back and turn left again. So there's a second change. Right? 2. How many times does it change?
Well, like it changed on the first curve, and then to the middle.
Now, as soon as I get in the car, I'm turning left. Do you agree? I'm driving on this. This is a road. This is not a hill. This is a flat picture of the map. It's like this, yes? So I'm turning to the left to begin with.
Yeah.
Right away. There's no straight part of this at all. My steering wheel is to the left. There might be a tiny bit, but it's left. Right around here, I start turning to the right. Yeah. And then right around here, I start turning back to the left. So it changes twice, 2 inflection points. Do those points exist? Hell yeah. There's no discontinuities in this graph, right? So, and it starts concave up. Do you agree? Do you see the smile? Now I'm looking at it like it's a hill. Do you see the smile on the left? And the frown in the middle, that's concave down. And the smile again on the right. Yes? So I know what's going to happen with this test now completely, right? All right, first step, find the first derivative. On your mark, get set, go. Find me the first derivative. Not too tough, is it? Pretty simple. Derivative, right? E to the x has a derivative of itself, but I got to get the derivative of the inside, right? Anybody get there? Anybody have this? Nice. Nice. Yes, Maria, yes. Nice. Kirk, yeah, nice. Engine, yes. Nice. Nice. Good, so that's my first derivative. When I do a second derivative test, if I do the whole thing, which I will have you do often, I want to find the critical values of the first derivative to use as test values in my second derivative. And so the only critical value here is a 0, right? Do you see that? When does this thing equal 0? When x is 0, right? So C1 equals 0 is the only critical value for f prime. Good. Then what do? Find the second derivative. And if you notice, I'm going to need a product rule here. My first function is negative x. The derivative is negative 1. The second function is the original function, e to the minus x squared over 2. And the derivative I already found, right? And when I found my f prime. So negative x e to the minus x squared over 2. I am doing a product rule to find my second derivative. And I see I get what, x squared e to the minus x squared over 2 minus an e to the minus x squared over 2. And I want to factor that because it's easier to find my critical values. Look at that. Aren't they nice critical values? Yep. So we see the critical values are plus and minus 1. Agreed? I'm going to call those C2 values. Right? C sub 2 meaning second derivative, C sub 1 criticals of the first derivative, right? How we doing here? You gotta, I'm your Uber driver, you gotta let me know. If I'm going too fast, you gotta slow me down. The only thing I won't do is change the radio. I'm in control of the music when I'm driving. We okay? Roger, yes? Nice. I'm going to do a sign table for my second derivative test. I know the domain is everything, right? I can see it on the graph. It goes out infinite. There's no discontinuities anywhere. I know my critical values are negative 1 and 1. And I know I want to test at the critical C1 value. I want to test at 0, right? But I want to test something to the left and something to the right as well. So I'll test negative 2, and I'll test at 2. Now, I don't actually have to put... Yeah, Kirk, what's up? Yeah, exactly. Yeah, C2, yes. Critical values of the second derivative. And you could write it out. I don't care how you do it, right? You don't have to call them C sub 2s. That's just me. I'm trying to put a little extra into the name so you know it's coming from the second derivative, okay? And again, so I teach you a process. You got to make it your own, right? I show you a step-by-step. You have to be able to write it down so that you actually understand what the hell's going on, right? You want to be able to read it during the quiz or test and know, oh yeah, this is what I do next, right? I don't need to actually plug these numbers in because I can see already from my curve that it's concave up, then concave down, then concave up again, right? But you're certainly welcome to plug them in, right? Like f double prime of 0 is what? E to the minus 0 squared over 2 times 0 squared minus 1. That's a negative 1, right? So you're welcome to plug them in. You don't have to. You're in calculus. I know you know how to plug in numbers to a function, right? Nice. I need to do a couple of things with my critical values. I need to make sure the points exist, right? And I also want to make sure f of 0 exists, right? So, but I found, what is f of 0? 1? Yeah. I know f of 0 is 1. And I know f, what's that?
How do you know F1?
Because I'm pretty good at plugging in 0 into x. Yeah, yeah. So, and I can plug in my plus and minus 1 into into the original function 2. That's e to the negative plus or minus 1 squared all over 2. That's e to the minus 1/2. And I like that as 1 over square root of e, right? Notice I'm plugging in my first derivative critical value into the original function to make sure it exists. And I'm plugging my second derivative critical values into my original function to make sure they exist, right? Because second derivative will tell me about local min or max and inflection points. All right, conclusion, ready? This is the worst part, right? So the conclusion is, I know f double prime of x, f second derivative, is positive. Here you go, Min, on minus infinity to negative 1, union 1 to infinity. So there's two places where it's positive. I put them together with a union symbol to name that interval, right? We did all that interval stuff in pre-cal and algebra 2. We had to write everything as intervals, right? Yes, Min, you with me? Okay, so f double prime is positive on that interval, so f is concave up on that interval. F double prime of x is negative on the interval minus 1 to 1. By the way, it's always open interval. Increasing, decreasing, concave up, concave down, always open intervals. Never a square bracket, right?
Wow.
Always. Because when you're at the end, you can't tell me if you're increasing or decreasing, you're stopped. But if you're in between, you're increasing. But if you got to the end of it, you're not moving anywhere. So how could you be increasing or decreasing? Kirk? Yes. Yeah, so I didn't bother checking those. You're saying here, right? Yeah, I didn't bother checking those because I knew I was concave up at both ends. So I pretended I put those values in because I knew the second derivative had to be positive there. You see what I'm saying? So I'm saying to you, I know you know how to plug a number in. So, but do you really have to plug it in to know that the second derivative is positive at those 2 points? No, because you know it's concave up. Right? Is that making sense at all? Yeah.
What does the U actually mean?
Union means this part and this part put together. F double prime is negative. No. No. There's a French system way to do unions that I would accept too, but but that's the intersection one. It would be a V. It would be yes. And that's an OR. And that's my symbol is an OR. My symbol is OR. Your symbol in Mandarin, this is the OR.
Yeah.
The V.
Yeah.
Yes, you can use your V. That's fine. Use the V. And that's an intersection.
And then for that, what?
That's for an and. This is an OR.
This is an
OR.
Why is this an OR?
Because I can't be in this set of numbers and this set of numbers at the same time.
But like,
I can't be less than negative 1 and bigger than 1 at the same time. It has to be an OR.
so they are positive at the same time.
The concavity, the derivative is positive.
Yeah.
It has nothing to do with how I'm saying what numbers are we talking about.
But
I'm
you
s-
are talking about a function.
I'm talking about the domain. I'm talking about the x values. I'm saying the second derivative is positive on those numbers. The numbers that are less than negative 1 and the numbers that are bigger than 1. Those can't happen at the same time. So we use the OR symbol in between. When and is an intersection, right? So I'd have to have two sets of numbers that are overlapping to use the intersection symbol. So it won't happen in this ever. So f is concave up on the same interval. F double prime is negative on the numbers between -1 and 1. Yes? So f is concave down on -1 to 1. F double prime changes signs, and I don't care positive to negative or negative to positive, at x equals plus or minus 1. So plus or minus 1 comma f of plus or minus 1, which was plus or minus 1 comma 1 over the square root of e, are inflection points. Right? I need the second derivative to be 0. I need the function to exist, right? And I need the second derivative to change signs in order to have an inflection point. F prime of 0 is 0. F of 0 is 1. And f double prime of 0 is less than 0. It's negative, right? So 0, 0 is a local max. There it is, the whole second derivative test.
Now, we need to write a conclusion.
You must write a conclusion. If you want all the points, write a conclusion. If you don't want all the points, don't write the conclusion.
What does it say? Inflection?
Inflection points, yes. Inflection, I-N-F-L-E-C. Inflection.
Say is a real max.
Is a local max. Sorry. Kirk, what's up? Yes, concavity. Changes concavity and must exist, though. Yes.
Are you going to have to write a conclusion on the homework?
Yes. Thank you. Good question. So the process, and you'll actually read the answers. The answers is the conclusion only. If you read the answers to section 4.3, you'll only see the conclusion. It's not going to show you the derivative or the criticals. It's just going to give you intervals and points. Kirk? Yes. Yep. I could. Again, so you'll see if you do enough problems, sometimes you'll have critical numbers of the second derivative, but they won't exist on the graph, so there'll be no inflection points. Like, for example, 1 over x, right, is concave down on the left and concave up on the right. But there's no point where they change, where the concavity changes. There's a partition where it changes, right? X is 0 is where it changes, but there's no point there, so there's no inflection point. Is that making sense a little bit? Yeah.
What do you write here?
Man, one more time.
So, F prime.
F
Any F prime.
F double prime?
Yeah.
Yeah.
Change signs at
X equal plus or minus 1.
and that so that one are what's the word that here?
Are inflection points. Inflection points. Yeah.
And I can call it IP.
Yeah, the book does, right?
So we can write it out.
Sure. I'll let you do whatever you want. I don't care. Okay?
And for the last one, I mean like F prime F0 prime equals 0 and F0 equals 1. And why does it make 0 a local max?
Oh, it's not 0, 0. It's 0, 1. Sorry. Thank you. 0, 1, right? f of 0 is 1, so that's the point 0 comma 1 is the top of the hill there. You see it? Right? 0, 1.
And why does it make 0, 1, 0?
Why does it what?
Why does it make the 0, 1 is a local name?
So when the second derivative is negative, negative people do what? Frown. Negative people frown. So that point,
What is from?
unhappy,
Oh,
you know? Oh, yeah. Frown, right? Smile. Yes? Frown. So it's at the top of the hill. When the second derivative is negative, it has to be on something that is concave down. So it has to be at the top of a hill.
yeah, but like why?
You got to go back and read my step by step for my
Wait,
second derivative test.
That 0 and 1 is come with the
Yes.
f function, right?
Yeah. Yes. The original.
So-
I always get the actual point from the original function. Always get your points from the original function. Where did I get the 0 part of it from? From the first derivative. It was a critical value of the first derivative. First derivative tells me about local mins or maxes. So does the second derivative. Read the step by step again, okay? All right, good. All right, here we go, new stuff. I want to stop that recording and start a brand new recording for this piece. We're going to do another section of chapter 4 today. At class on Thursday, you're lucky you missed it because it was almost 2 hours of me doing a step by step and writing everything out.